phenomenon, the topic is actually, I got into this one at my last sabbatical about 7 years ago when I visited Australia also for 4 months. And then this topic became very interesting to me. So I spent last 7 years to get the paper published this time. It's fantastic. So I want to share about what I've learned in last, 7 years to see how it works out for this kind of cross phenomena, and also during the process we found that we have to also make this kind of Zentropy prediction, and we can also talk about that too. Okay, so I added a series, the word series in the title, series for cross phenomena and the Zentropy. Again, my name is Zeke Liu from Pennsylvania State University. Here's the website of our group. Okay, cross phenomena. So what is cross phenomena? It's basically the internal response of a system to external stimulus. Or you could have more than one stimulus, so you can stimuli. So for example, if you change temperature, right, get temperature gradient from external control, internally, you could have something is going to happen. So could be the electron migration, because of some electricity. Or the diffusion takes place, you get thermal diffusion, or they call it thermal transport. Or if the external control is electric field, then you could have the heat conduction, you got the electrocaloric effect. For example, people are trying to make refrigerator by electric field, the current, instead of the compressor we have. In diffusion, you get electron migration. That's a very important issue in electronic devices. Or you get deformation, like electromechanical, right? Let's look at the transducers. And you can generalize this one. It's external, it's potential. So it's the temperature gradient, electric field, or the pressure or stress. You can do strain too, but it's much harder. Stress is much easier. So most of the time, externally controlled variables are potentials. Then internally, it's going to be conjugated variables. So all the changes here we talk about are molar quantities, which it's size dependent, right? Consider this one. So the first one is electrons, and diffusion is atoms, heat conduction the phonons. And the example you have the other examples, in addition to this electric field and temperature gradient, you also have the uphill diffusion. Okay, that's not by temperature gradient, but by the chemical gradient. And thermal expansion, that's volume change as a function of temperature. So they're actually all cross phenomena, but most of the time, the first two are top of the more than the last two are the ones. Okay, so because this phenomenon, of course, is observed many, many years ago, and Onsager in 1930s, he developed a theory. Now we call it Onsager reciprocal relations, ORR. So what it means is that he first postulated an equation called a flux of a quantity, Ji, is proportional to all the driving forces you have here with the prefactor, or the kinetic factor you sum together with negative sign. So that's his postulation, and it's widely used in the literature. And he proved that from a mechanism argument point of view, say that Lij equal to Lgi. That means the matrix of this kinetic coefficient is symmetric. So that's basically his theory. And he obtained the Nobel Prize because of this theory. So this theory is actually not really based on fundamental laws. It's phenomenological. It's observations you have. And as pointed out by Max Hillard, and this is not from fundamental physics, first one, and also by a very well-known kinetics book by the MIT professors, 3 professors published the one. And they mentioned in the book that these equations, or the relation here, are not from first and second laws of thermodynamics. So that means this equation, which is seen everywhere in all the textbooks about the kinetic processes, is neither fundamental, not from the thermodynamics either. So then the question is that how do we know it's correct, right? How do we know it's correct? It turned out in the literature is already quite some discussions on the questions. So I'm going to propose three questions here. Pose the three questions here on the OR on reciprocal relations. First one is that think about this one, right? If that kinetic coefficient matrix is symmetric, then you can diagonalize it. If you diagonalize it, so what are the components of the eigenvector? That question never be asked, not answered in the literature. Can they be derived from the first and second law of thermodynamics? That was a question by the kinetic book. Okay, so that's the first question. If you can diagonalize it, then what's the result of that one? The second question is more serious, is that if the driving force gradient for that molar quantity is equal to 0, but the flux is not equal to 0, right? Because if flux of that quantity is 0, that means all of them must be 0. Okay, but that's not too bad. If all the off-diagonal terms are 0, that means the matrix is diagonal. That's pretty good. Okay. So, but this question means that a molar quantity could even flow, right? Could change. There's no gradient for that conjugated potential. For example, you can heat flow without temperature gradient. If you have other gradients, for example, unless this one is diagonal. So the third question is for the entropy production. The entropy production for that flux and for its potential gradient multiplied is equal to 0, okay, when delta phi I is equal to 0, right? However, the Ji doesn't have to be equal to 0 if the matrix is not diagonal. So that means the matrix has to be diagonal. You want to have all of them work, right? So actually, look at this one. Is that basically if you want, if we want, that means no driving force, no flux, okay? And no flux, no driving force, no flux, no entropy production. So that means the matrix has to be diagonal. Of course, if the diagonal is symmetric, right? So that was the question we had, and to answer for this OR. So about 7 years ago, I started looking at this one when I was talking with my host in Australia about the thermal transport problem, thermal diffusion problem. Okay. Of course, you know, in order to solve these three questions, then we have to derive the driving force eigenvector. So this matrix is diagonal. So can we derive it? That's the question I've been thinking about for the last several years. Now I think actually I figured out just before the COVID, I gave a talk in Spain, no, in Greek, for a diffusion conference. And that was the time I solved the problem, but they did not formulate it properly. It took me 2 years to formulate it properly and have that paper published. Of course, this is not new, right? People have questioned. People questioned this Onsager relation a long time ago. One of the very significant one is actually by Clifford Chester back in 1960s. Okay. And in that paper, it's a very interesting paper. He pointed out the OR itself is self-contradictory. Okay? Because the force and flux are not defined. If you don't define them, you can really not say whether the matrix is symmetric or not. That was a very interesting argument there. And then published a lot of papers too after that, like in 1962, 1969, in the book about irrational thermodynamics. And when I was looking at this problem, I found a very interesting paper by Kaczynski and Grubella. And in their 2013, that's many years later, of course, between them, many papers published too. And they point out the flux for diffusion, a component of J, the flux is only proportional to its own chemical potential gradient, nothing else. So of course, that means the matrix is diagonal. So that was very interesting. But however, in the paper, they did not say the Onsager relation is not needed. I wrote a comment on the paper I published last year before my paper. And I come to their work, and I found that they started with a good equation, but they got something wrong for the conclusion. All right, and then my PhD advisor, John Ogren, he just wrote. We have been discussing this one in the last several years, and turned out back in 2006 or something, he had a presentation on this issue, on this topic, and then we discussed it. After our discussing, he wrote a paper on this one. Okay, it's been just published now, in printing this month, last month, in this journal. And he pointed out for the diffusion aspect, the Onsager reciprocal relation is basically not needed. It turned out when Professor Ogren, John Ogren, did his PhD thesis, he developed a dictionary software, as many of you know that. And in his work, he already showed this equation. Okay, already showed the flux of a component is a proportion to its own chemical potential only. That was his equation. By that time, it was not discussed with respect to the Onsager relation. So it's basically the same equation as this one. As in 1992, he published that paper, but the equation was done much earlier in 1970s in his PhD thesis. Okay, so now the question is that can we go one step further to derive that equation from the first law, or from combined law of thermodynamics? So that's what I did in the last several years. I think I believe I succeeded. That's why I got the paper written. Okay, so what it means that I want to start with entropy to talk about thermodynamics. The entropy of a system has three components, which we usually do not talk about. When we talk about we talk about first term most of the time only. The heat divided by T, heat change divided by T. Because we usually talk about a closed system. If you use an open system, you have this entropy change because each component brings entropy, right? And if for non-equilibrium system, if you use non-equilibrium, then you have the entropy reduction due to the internal processes. Now, if you take the first law, you have Q, you have work, you have the mass. Again, in most of the textbooks, we only talk about the first two terms because we talk about a closed system. That's really the problem, because if you talk about a closed system, you cannot introduce chemical potential. And that's why in most of the textbooks, chemical potential was introduced suddenly at the end when you got free energy. So that's extremely confusing what it means, what is the meaning of the chemical potential. But if we start with open system, then chemical potential definitely becomes straightforward. Okay, so now we just replace dq with delta q here. And then you got this equation, TdS and dW, and now you get a chemical potential now. What's chemical potential? It's basically UI minus TSI. That's chemical potential. Then you get the last term is entropy production. So now you can group them together. You got I follow Marcellus' book. It's Y is potential, X the molar quantity. Then you have the entropy production. Okay, so this is really complete combined law. However, one of the huge problem in our textbook is that I would not say all textbooks, but most of the textbooks did not have the last term in their combined law. Why? Because they talk about equilibrium system only. Okay? Why we only talk about equilibrium system only? Because in the paper by Gibbs, he dropped this term. He only talked about equilibrium. So actually, if you drop this last term, if you only have the first term as summation here, it's for equilibrium system only. So that many people don't realize that. Okay, now, so how do we do this internal entropy production then? Then that means you have a lot of processes, right? Use the d psi j, that's one process, and then the driving force. So the entropy production is T times DIPS, that is the energy term. It's equal to the driving force for that process and the change of that process. And now what's the driving force? Now you can know that. Actually, the driving force would be temperature gradient and the chemical potential gradient, but it's for internal variables. It's very important to realize that this here is all external variable, except entropy. Because entropy has both external and internal variables combined together. So then you can extend this worker to hydrostatic work, or you talk about stress, You talk about the electric field, or you can talk about the magnetic field too. So that's all the cross phenomenon, and because of the different work, interact each other. Okay, now, so you go back to this equation right here, right? So basically, these are internal processes in the system. So that means we're talking about the reciprocal, the cross phenomenon is that it changes some potential from outside, as this one, and the internally something could happen, right? So that means we should use this one to derive our flux. So that's really the flux equation should be derived from these internal processes. So how do you do that? Okay, so we can do that as well. So we have entropy production. Now we talk about the process. We have the gradient, right? Time, the rate. So the entropy production rate times temperature is energy as per volume divided per volume. And then you can replace this one if we consider one process. One internal process would be dj times the d cosine. Now it has rate here as the rate of the change of that internal variable. And the volume is just the area times the thickness. Yeah. Now we can do some just very simple math. We can move this together, move that together. Now we get the gradient of the driving force, that's delta y cosine, and then d cosine with dot, that's the rate divided by a. Well, this one, this is the flux, right? This flux. Okay. So now we can define the flux. Okay. Flux would be equal to the d cosine dot divided by a. Okay. And then this process we can say it's going to proportional to the driving force, right? Driving force, because this is driving force drives this process. Okay. Then we have a coefficient there. Of course, in the reality that it's not always linear, right? But you can always make the time shorter or make it linear. They do integration to get nonlinear properties, behavior. So linear function is always right because you can do the integration along the path, get nonlinear behavior. And now what it means, now can write this one. That's exactly the entropy production now, right? Say the flux, right? Flux, okay, times the driving force. So that means the error, the kinetic coefficient, error cosine j times the gradient of the potential square. So this has to be always positive, right? It's positive, right? Because error is positive and square is positive. So you get a positive entropy production. That means based on second law, that process is possible. So when it becomes not possible, is this equal to 0? So when it's no gradient of the potential, of the conjugated potential, then it becomes 0, no entropy production. So it looks good. So second law is good, right? So we'll solve our three problems related to the Onsager relation. Entropy production would be no driving force, no flux, no entropy production. And the diagonal, the kinetic coefficient matrix is diagonal, is symmetric. So for this derivation and all the three questions we raised, not only by me, but also in the literature, and are addressed. And this equation is derived from the combined law. All right, so we call this theory of the cross phenomenon. So how can we use this one to understand the cross phenomenon, right? Cross means temperature, you get an electron conduction. There's some electric property. What does that mean? Okay, let's start with this equation, a flux equation. Now, this flux is very important now. It's not from the phenomenological. It's from the combined law, from the internal processes. Okay, then we say this potential gradient is a function of all internal variables, right? I put cosine here as a subscript, that means they're internal. So it's a function of its own conjugated molar quantity. For example, if this temperature, this will be entropy. If this pressure, this will be volume. Okay, if this chemical potential, that will be a component. And it's also a function of other potentials, right? Okay, for example, if this temperature could be also a function of pressure, also a function of electric field, or a function of chemical potential. And it could also the other molar quantity, right? For example, temperature gradient could be, chemical potential gradient could be a function of another molar quantity, volume, for example. And then there may be many processes at the same time happening. So it could be another independent internal variable. So you have a conjugated internal variable, long-conjugated internal variable, an external controlled voltage, potential, and externally controlled molar quantity. So what does that mean? That means we can need to change this gradient to a gradient of all of them, right? So I'll take the first one, that means the derivative, that is expansion there. That means a gradient of the molar quantity, conjugated molar quantity, gradient of the other potentials, gradient of other molar quantity, gradient of other internal variables. So that was cross phenomenon comes in. This is the definition now. So that means we can solve them. So what do we need? Why we need to solve all the derivatives, right? So now we have seen this derivative a lot. There's potential to molar quantity. Okay, we see this one a lot. This is also a potential to molar quantity. I'm going to show a table on that. But this one is very rare for us to see. I have not seen any textbook to really discuss this quantity, what it means. Okay. So the TCB theory, I got the TCB theory of cross phenomena, is that flow of a molar quantity is solely due to its conjugated potential gradient. This one here. Cross phenomena is dependence of this potential on other variables. For example, if the chemical potential of electron is a function of temperature, then temperature will drive electron diffusion. So that's some electricity. Okay, so if you look at the table, here, these are all the potentials we have. We have temperature, stress, electric field, magnetic field, and chemical potential. And these are the conjugated variables, conjugated molar quantity of entropy, strain, electric displacement, magnetic induction, and the moles. Okay. So now you see we have the diagonal terms that's between the conjugated variables. That means these two are the pairs. Okay. So these quantities will always be positive in a stable system. If the system is stable, it's always positive. Then we got this off diagonal terms, right? So this, for example, some expansion is the strain of the volume to the temperature gradient. So, but these two are not conjugated pairs. So that means the off diagonal terms are between long conjugated variables. So they could be positive or negative. Okay. So why this diagonal term is positive? Because the stability of a system requires they be positive. But the stability of the system does not require the off diagonal terms to be positive or negative. So the nature, if you don't give constraints, the nature does whatever it wants to do. So sometimes positive, sometimes negative. Okay. The blue quantities are the new quantities we introduced in our work. Okay. So this Ni to T, right? The moles to temperature, what does that mean? It's actually some activity. That's chemical reaction is like that. Okay. You can think about the stress reactivity. That's how the stress affects chemical reaction, how the stress affects the chemical reaction, and how electric field and magnetic field, right? And this one's very, very, very important. This we call a thermodynamic factor. So what does thermodynamic factor do? It does. Well, it affects our diffusion. That's why the thermodynamic factor is in our diffusion coefficient. I'm not going to show that one here. It's the mobility, it's the error parameter times the thermodynamic factor give us a chemical diffusivity. Okay, so this one we have seen a lot of them except the blue ones. Okay, the blue ones. Now I mentioned about the potential derivative. So that means I can replace the rho by potential. So I have this potential, as I mentioned before. I have more potentials here. Same potential. Of course, temperature term is 1, right? So the diagonal term is 1. But off diagonal is that's the stress to temperature gradient. That means how temperature affects the stress of the volume. That's some expansion, right? But it's not something, it's stress, not the volume, it's stress, right? And they make a lot of these new quantities here. A lot of new quantity. And even more interesting one is that so much transport. What is so much transport? Basically, the chemical potential as a function of temperature. As a function of stress, because stress transport, with electrical migration, magnetic migration, and this is cross diffusion. Okay? And if we use the Maxwell relation, we find that we can actually convert them to the molar derivatives. Okay, so this is all entropy derivatives. We call it partial entropy, right? It's all partial entropy, but this is not a partial entropy anymore, right? It's not an NI, but it's a stress, a strain, and so forth. And they're equal. So it just turned out so interesting that, and this quantity is very easy to measure. This is quantity we want to calculate. Okay? Now you see that we need entropy. Okay, that's what a Zentropy is about. So this is all about a cross phenomenon. Okay, all these quantities we have on the blue quantities are the one we talk about cross phenomenon. We can measure them. But however, the calculation is very hard. It's extremely difficult to calculate how sigma ij changes with temperature. However, we can calculate the entropy change as a function of epsilon. So this table is beautiful, beautiful combination of theory and experiments, and it was invented by, discovered by Maxwell, many years ago. I want to mention, so this is one, and also of course, if you look at the previous table, you see this one, right? So also Maxwell relation. This is also Maxwell relation too. It's YA to XB equal to YB to XA. So that's why this matrix is also symmetric. So that's fundamental. So it's very different from Ansak's symmetry concept. All right, so application to the TCP, as I mentioned in the paper I just published this year, I talk about all kinds of systems we have. So again, it's very important. Okay, is this YA to YB? It's two potentials. You take any one, the temperature, a stress temperature, and we talk about the electric field temperature, right? And so forth. And again, the cross phenomenon is YB gradient drives the flux of XA through YB gradient, YA gradient. Yeah, so because these two are the conjugated pairs. So, for example, the thermoelectric for transport of electrons or holes is that the change of the internal variable is the gradient of the electron concentration gradient or the hole concentration. Okay, the external field is temperature gradient. We assume there's no diffusion of other components. Thermal diffusion. Now instead of the electrons, we have the components. Again, the driving force is still delta T. Okay, but delta T is not the direct driving force; it's the chemical potential is driving force, and this one is the effective chemical potential. Electron migration is basically when you apply the electric field. Okay, the diffusion takes place. Okay, and the electrocaloric effect is that its entropy is moving, and the effect of the electric field. This one is very, very important. Electromechanical effect is transporting electrons by the stress field. Apply stress field, and then the electron starts to move. And the details are discussed in the paper, so I don't think we need to go through all of them details for that. But I do want to show one example. Is that a couple of years, some years ago, we got a project with JPL to study the thermoelectric materials. So now you see in thermoelectric materials, the electron diffusion. You have the mobility, you have the gradient of electron potential, chemical potential. And this chemical potential of electron is a function of concentration of electron and the temperature. You do two derivatives. Now I get two coefficients here. One is this one thermodynamic factor. That's basically the second derivative of the free energy to the electron derivative. And then this is one, it's a partial entropy, right? Remember that mu E to T, it basically is the entropy to CE. That's the partial entropy of electron. Okay, now we talk about when we do measurement of some electric material, you do steady state without current, is J equals 0. Then you got a seebeck coefficient. Okay, turn on. So seebeck coefficient is completely thermodynamic property. It's equal to minus entropy, partial entropy electron. And you can do the whole two. Oh no, from this equation directly got the parity coefficient and Thomson relation. Okay, directly from this relations. So the JQ here is heat. The electron carries heat. Okay, you can calculate this one. So you get an electric relation. Beautiful. Completely derived a parity coefficient and a Thomson relation without any assumptions. And you go also calculate the seebeck coefficient of the p-type, which is the hole. And then now you see the seebeck coefficient of the holes is positive, as partial entropy of holes. The partial entropy of electron with the minus sign is negative. So that means the n-type of seebeck coefficient is negative, but the p-type of semi-electric seebeck coefficient is positive. Now this is our calculation. We did a few, let's see, that's 2018. We did the electronite. You get these negative ones, you get the positive ones. Okay, by doping, they change to p-type to n-type. And the tin selenide is positive. Okay, so it's whole type, it's whole. And then for the lanthanum telluride, you can see by changing the different defects concentration, the off-stoichiometric, you can see with different doping concentration, carrier concentration, and the prediction just unbelievable. There's no fitting parameters. It's all from the thermodynamic calculation entropy of the electrons. I do want to mention that in this diagram we compare it with the Boltzmann transport method. Okay, this data here, and they are way off from the experiments. Particularly those ones, you cannot predict them even from the Boltzmann transport theory, because there are some self-assumptions here, relaxation time, and quite a few assumptions here. Okay, so now you see the entropy becomes so important, right? So we have been working on entropy for quite a while. So now I will share with that entropy production and entropy. How do we do that? So this is the question I showed before. So the internal process, one internal will generate entropy production. Then you have temperature times entropy production give you the energy. And based on second law, all of them has to be each individual independent internal process must produce entropy. So it must be positive, or 0 or be equilibrium. Okay, now for entropy itself, it turns out is quite complex. So it's actually a lot of different ideas. So we know thermodynamic entropy. We know that if you measure heat capacity, you do integration, you get entropy. That's the thermodynamic entropy we typically introduce, like the Q divided by T, right? In the first equation I said before. But we also have statistic mechanics. If you look at the Boltzmann entropy, it will be Kb log omega. Omega is number of configurations. But if you look at the Gibbs derived equation, is Kb minus Kb summation of pk log pk is the probability of a configuration of a microstate summation. When all of the microstates have the same probability, it reduces to Boltzmann entropy. Okay, 1 over pk equal to omega, basically. So these two are consistent. The first one is for all the microstates have the same probability, and the Gibbs entropy is that when they have different probability. And when we have also the quantum mechanics for entropy. Okay, so we have these thermal electrons. You can calculate one from the distribution with electrons, or you can calculate phonon. Okay, so use Fermi-Dirac statistics, and use both Einstein statistics. Okay. So now we see we got this Fermi-Dirac, we got both Einstein, but it gives. We can also get entropy, but how do we connect all of them together? Okay, that's what it really Zentropy does. So I will talk about Zentropy here. So they're all part of the entropy. Okay, but none of them is complete, except the thermodynamic one. That's the key message. because the thermodynamic one, you do measurement, right? So measurement with the experiments, it captures all the entropy in the system. But when you try to do statistical mechanics or the quantum mechanics, you can also think statistics too, but different statistics. And they only capture part of the total entropy. Why put them together in order to compare this, the statistical quantum with the experiments? That's basically the entropy concept. So let's see how we do that. So we have this microscopic entropy, I will call it, actually call it Gibbs entropy. Is that for system entropy, we have this one, right? K minus KB, a summation of P log PK for different microstates. So that's one we're talking about most of the time. It gives distribution. However, each microstate has its own entropy, right? It's not zero. Most of the state is not zero. Okay, so that means we have to actually include that one too. So now you see, I have two terms now, right? The first term, that's Gibbs distribution. The second term is Pico SK. So each of them has its own entropy. So that's basically the entropy concept. Of course, each microstate can be analyzed in the even more smaller scale, right? So you get a sub-microstate, right? So you continue to go all the way until you go to the electron or the quantum scale. So this is really the integration of all of them. Then what it means is that this part would be from the Gibbs distribution, talk about the classical particles, a classical state actually, not particles, classical state. And this would be the contribution from the lower scales, not from quantum mechanics. Okay. But however, we found one problem when we got this one. So if you take the Gibbs statistical mechanics, like in Landau's book, and they take it for energy like entropy like this, then they get this partition function. So it's very, so in this case, they have EK, the total energy or the internal energy of that microstate. But however, if you take our equation, you get a partition function has to be an FK instead of EK here. So it has puzzled us for many years. We don't understand why it would be different. Okay. And then, well, you know, maybe because COVID, I got more time, not to travel. Actually, to Cambridge is my first travel in 2 years. And it turned out in Landau's equation, it's the implicit assumption is that SK equals 0. Okay. If SK equals 0, EK equals FK, right? So TSK, that's 0. Okay. So how could be SK equals 0 for a state? That is, there has to be pure quantum state. You only one state, cannot go to two states. Okay. So that means if you take the state here is pure quantum state, then this equation is okay. But in the reality, when everybody uses it in the literature, nobody goes to pure quantum state. Why? Because you cannot solve it. Like you have to solve Schrödinger equation for a big system. Now, if you take a density function theory, each microstate is not a pure quantum state anymore. It is a multiple quantum state. So that state has entropy. So you have to use this equation, basically. So what it means is that in the practical application of statistical mechanics, we have to use this FK instead of EK. That's our conclusion. Okay, so that means now we have three terms here. We have thermodynamics from the experiment. We have statistical mechanics for the Pico log PK with Gibbs entropy. We have quantum mechanics, predict SK. That's have the electronic contribution and plus the phonon contribution. So now with this, we can actually predict the critical point. Critical divergency, and it has not been predicted before. You cannot predict from quantum mechanics because they don't have one term here. You cannot predict from the statistical mechanics alone, okay, because you don't know how the PK changes with temperature. So actually, we also use this one to predict the quantum critical point where you have the mass divergence, effective quasi-particle mass. Okay, now in this case we had before, we show that the cerium, this is a temperature volume phase diagram. You can see that at the critical point here, the volume diverges. The particular sum of this expansion equal to positive infinite. Okay. And also you can prove that for the inviolate, the volume diverges negatively. because as I mentioned, B and T are not conjugated variables, they're going to change sign. So actually only this area, in this area, yeah, this is anomaly, negative sum expansion. So even far away from the critical point, because you have that factor there. You have this combination of quantum and the statistics. Again, this is experiment data, and here are the experiment data, and all the experiment data points here. Okay, so reason, as I mentioned, is temperature and volume. They are not thermodynamic conjugated variables, so they don't follow each other closely. Okay, so I want to mention that because Amit had one of my students to be an intern there. So we have been trying to develop the ecosystem of data tools in order to do this kind of work. And we are now creating a new database called the Ocean of Materials. We're in the development, should hopefully be ready very soon. And we have data generation tools. We have DFTK, that's Dr. Iwan, his work. Then Superfilm is the work by Adam Kuryevsky. He will be intern at the Los Livermore. And also Adam created the material property descriptor database. And also we have combined experiment data too together. Then we have data processing tools. We have PACAF SBA and also uncertainty quantification. This is in collaboration with the scientists at Oregon National Lab. And you know, we're not developing Zentropy a tool, so we can systemize the entropy calculations as I mentioned, and also the Zentropy application. We also do workshops. I use the nonprofit organization and Material Genome Foundation. Okay, so we can even move this one further to the entropy production information. So now this is for entropy production. Now you can heat generated. Now you have to think about is the process now, right? Not the total entropy. Then you have the nutrient consumed by the system, the waste generated by the system. Then that's information destroyed by the system, by the process. And we found this is fascinating because there's many more papers now. I talk about the entropy and the information. Of course, it always started in the 50s too, by Shannon entropy too. But it's actually very close to this one. So one of the very exciting things for me to come to University of Cambridge is Stephen Hawking. It's here. He developed a entropy for black hole. That equation, the entropy is proportional to the area of the black hole. I find it fascinating. I haven't figured out how it connects to our Zentropy theory yet. Maybe next time I talk with you, I give you a theory as a connection with Stephen Hawking's entropy of black hole. Okay, I want to get summary here. We derive the flux of molar quantity by the first law, combined law, and we postulate, we prove that actually, the flux of a molar quantity is solely driven by the gradient of its conjugated potential, which is derived from the combined law of thermodynamics. But we have to remember, we have to put the entropy production in the equation, not like Gibbs did, remove it. Then it doesn't work because they cannot derive it. And the theory of cross phenomenon stipulates that the cross phenomenon originated from the dependence of this potential on non-conjugated variables. And they get all kinds of cross phenomena, which are shown by that table I have. Two tables. And the Zentropy theory is discussed in terms of the entropy contribution from quantum mechanics, statistical mechanics, and it can predict the emergent behavior, right? That the critical point is the extreme of the emergent phenomena, including both positive and negative divergency at the critical point. There's no feeding parameters. It's completely predicted from the quantum mechanics and the statistical mechanics. With that, I want to thank you for your attention. Thank you, Amy, for giving me the opportunity to present here.
Professor Liu, thank you so much for sharing these interesting results. The talk is now, I'd like to request people in the audience to applaud the speaker. The talk is now open for discussion. Please feel free to post your questions in the chat box, or you can unmute your WebEx and ask them directly to Professor Liu. Since I don't see anything in the chat box, let me start by asking pretty naive questions. So my question is mostly related to the initial part of your talk, where you were introducing on-saga relationship. So from my understanding, this is all still a linear theory. And do you know how important are nonlinear terms? Like, for example, if you add a second order term, yeah, like for example, here, the first equation, you can go ahead and add a second order term where you have derivative of y for two different effects, and correspondingly, you will have a coefficient. How important are terms like that with the compared to the effects that you are showing here? Has anybody looked at things like that, or maybe they are not important?
I discussed this one in my paper too. The second derivative is only important when the first derivative is zero. If the first derivative is not zero, second derivative is not important.
I see.
Okay. So, but you can always make it smaller enough that you can always make that z smaller enough, and so that's always linear. But so the nonlinear comes in way into the integration. So that means all the quantities you have here will be function of the path, the position, the variable. So then that way you can actually count the nonlinearity.
Okay.
But if the system is at a critical point or equilibrium point, right? If the stable equilibrium doesn't matter. It's at the unstable equilibrium. The first derivative becomes zero. Then second derivative becomes very important is because it's negative.
Yeah.
It's negative, that's what you call the dissipated structure. Because if the system depends on the disturbance, depends on the path, a little bit of disturbance on each direction, the system can go completely different way.
Okay.
That's bad. If you talk about if you have only two directions, you get a bifurcation situation. But if it's truly unstable, you have infinite number of directions to go. That's where the non-linearity becomes very critical.
Okay.
But again, what it means is that you have basically still have to know the shape, right? Know the shape. Then see which direction it goes. They're completely stochastic.
Okay. Okay. Yeah. Thank you so much. Steve actually has raised his hand. Steve, you want to go ahead?
Yeah, I was just to say, very, very interesting talk, Dr. Liu. I was very, very, very excited to hear about this when I saw your Zentropy paper come out. It was very, very interesting to read through. I was just wondering if you could touch on some of the technical challenges regarding, doing thermodynamic sampling using first principles techniques like density functional theory, because it seems like that's really the crux of the problem to kind of build these types of models is to effectively describe things like activity coefficients. So
that's the key. That's the key part. That's a great question. That's a major challenge, right? So how do you make sure that you have the sampled the important microstates? You don't have to sample all of them, but have to be important ones, right? That's extremely difficult. Okay, so that's one of the reasons we had in our previous work. In our work here, we sampled all the states. So you fix a supercell, there's magnetic states. So you do all kinds of magnetic configuration. So it's actually very interesting. In this iron-3 platinum, we have 9 iron items. So 2 to the 9 power is 512 configurations. Okay. But in this case, we actually did not do that. We only take 3 states. We take because cerium at low temperature is non-magnetic state, right? So in a non-magnetic state, high temperature here is ferromagnetic state. Then we took the AFM state between. We take 3 states actually predict the phase diagram. Yeah, but this one will have 512 states. So the solution is that if you get the key states, it actually works. You don't need to get all the states. That's the first one. But how do you know to get the key states, right? That's because it's not trivial. In this case, we just do all of them, enumerate all of them. That's right. But when you get a structure, not a magnetic, but not a structure change, how do you know you get all of them? That's why That's the exact reason we went to this machine learning and also this materials property descriptive database. So in this one, in the database now, we have like 4 million structures now. So you can generate a structure by substituting elements into any of the structures, create a new structures. Okay, so you can create all kinds of structures for that one. But then, of course, that's too many, right? You cannot calculate all of them. So how can you decide which one to calculate, which one to use? So then you saw some machine learning one, we can get the energy very fast. Then we can rank them. We only take the low energy ones, we forget about the high energy ones. Because the probability of the high energy ones is 0. So that's our approach. So our new tool we can develop, Zentropy tool, is going to be combining, it's going to combine the machine learning database, machine learning tool, and also as DFT as a backup. Because at the end, when you gather the structures, you want to get accurate energy, then you go to do the DFT calculations.
I see. I was also curious, is I think in previous work, your group has used things like SQS methods for sampling as well.
Yeah.
Is there room to incorporate some methods like cluster expansion techniques into this, or do you try to, where possible, just use some things like regular solution models or sub-regular solution models?
So the good thing in this one, we don't need a regular solution anymore. We don't need solution models anymore, so to speak. We can just calculate all the states for different compositions too.
Okay.
So we don't have to fit into any. We don't have to fit into any particular interaction parameters anymore.
I see.
But I go back to your question about the SQS. We actually, our database here is going to have SQS too.
Oh, okay.
We have something already in it.
I'd be interested to take a look. Thanks for letting me know.
Okay, thank you.
Okay. Any more questions for Professor Liu? Professor Liu, I have another question related to what you had on slide 19. So this is like the quantum state, and how relevant is von Neumann entropy here? Like given a density matrix, many people use von Neumann entropy here, where this P of k is essentially the density matrix multiplied by the log of the density matrix. Can you tell us a little bit more about that?
Yeah, we did a test. If you take the formula on the left side, again, you got all the quantities from DFT, right?
Yeah.
And we did magnetic transition temperature. For example, if you look at this diagram, if you increase temperature, you get a transition here, right? Okay. That temperature is offered by 100 degrees.
Okay.
If only use this equation.
So is that an uncertainty between the different entropy formulations, or?
Yes, because they omit the entropy of this one.
I see. Okay.
Yeah, we tested a few systems. We have one paper in the making for the oxides. Same thing. The temperature will be off by 100 degrees.
Okay.
Actually, that's probably one. You remember that? You probably know that in the DFT community, people calculate, our temperature is off by 100 or 200 degrees. I think that's why. That's one reason. So that means DFT alone is not enough. You have to put this term into it.
Okay. Sergey, do you want to go ahead?
Hello?
Yes.
Yeah, we can hear you.
Hi. So thank you for interesting presentation. There's one general question when you're dealing with systems out of thermal equilibrium. So you're introducing parameters like chemical potentials, which are in your case some continuous functions and this of coordinates in a system, etc. This requires a system like that. One should be able to define these parameters, thermodynamical parameters, and this means that your system should be not too far from thermal equilibrium. And then question arises, like, could you introduce explicitly criteria when your models are applicable, like what deviations from thermal equilibrium are allowed, and above some deviations, theory will not work. Yeah, do you have this criteria in your theory?
No, that's why look at this equation here, right? Look at the equation on the screen here, okay? You can always define mu I.
No, you cannot, this is thermodynamical parameter. You need to have some system which is close to thermal equilibrium, and you can.
No, you don't have to. I don't agree. I don't agree. You don't have to. You don't have to. Because if you frozen that system, okay? If you frozen that non-equilibrium system, now if you make an infinity small change of that system, that's how you define it. So that's what Marcellus called a frozen in system. Frozen system means that the energy you have is a function of the internal variable, non-equilibrium state.
But can you have a situation where the state is changing in a non-equilibrium way very quickly? So
no,
that
you can change it very quickly too. Okay, the reason because that if you take that, they can reduce your time step when you do the integration. Okay, if you reduce your time step, reduce your space step small enough, and then you can frozen that system and make that system infinite to measure its property.
I see.
Of course, now the trick is that you need to add that gradient term into your energy, right? That's why you need to add this last term here. You want to talk about total energy of the system, you have to add that term, which includes the gradient of your molar quantity, the process.
Okay.
But for the individual terms up here, you can well define them. So that means if the gradient becomes very big, your internal energy could be very big too.
Yeah.
But all the terms you had before can be is well defined.
No, and sorry, still, like, yes, you always can be solving like total kinetic problem with coordinate of all particles and energies at all interactions. But this problem in quantum mechanics becomes untreatable for number of particles approaching 50.
That's exactly true.
Yeah,
that's why you have. That's a great point. That's an excellent point. So you want to solve that problem. You have to use density function theory. That's why you have SK here now. That's why that's exactly why you can't use Landau's equation for the statistical mechanics. Because if you use his equation, you have to do all the states, all possible quantum states. You cannot do it because the system is too complex. You cannot solve all the Schrodinger equation. But if you take a density function theory, it works nicely because you put those things you cannot treat individually, you put in the SK. How to do SK? Then you just take the one we have top of the first equation here. Oh, sorry.
Well, I still.
Yeah, you see here, right? You see this guy.
You need quantitative criteria.
It's quantitative, yeah. So that's exactly
how far from equilibrium you are, something like that.
You can basically do anything, any far away. You can calculate basically liquid at 0 Kelvin.
If you are solving kinetic equations, you can be far away from equilibrium. but this does not work for number of particles rising. Yeah.
Yeah, that's
So
that's
then,
actually,
if you're trying to use some ideas from thermodynamics, it's perfectly normal. But you need to define how conditions when you can use some thermodynamical quantities.
you see, this is demonstration here. This is the instability, critical point, completely predicted. Critical point is the most extreme instability you could have. Divergency.
Well, it's not the only instability you can have.
Because you
Then,
have, see, here you have singularity of the property.
So Sergey, I think we should move ahead and perhaps
yes, okay.
you can reach out to Professor Liu via email, and that would be a better medium to continue this discussion.
Yeah, please. Let's discuss that one separately. I think it's a very interesting question, and maybe we can get some new out of it for discussing.
But related to this, Professor Liu, I had a quick question. So cerium, is this all done at the PB level of theory, or are you going beyond PB and doing some correlated theory to
Yeah,
do
this one basically means is that for here, all the anomalies can be predicted. Heat capacity anomaly and the magnetic change, magnetic magnetization, can all be predicted from these quantities.
From PB LDA type of theory.
That's right. That's right.
Okay.
The reason is because we're not starting with any equation of state. We start with the free energy.
I see.
So all the derivatives, right? That's actually two tables. All the derivatives can be calculated.
Yeah. So essentially, if you take a few steps back, what you are saying is that one can effectively explore the phase diagram by following these derivatives rather than simply following the state variables.
Yeah, that's right. This actually makes a lot of sense, right? Think about this one, right? When Gibbs derived his entropy, there was no quantum mechanics at that time. Okay?
Yeah.
When Landau got a statistical in place, the density function theory was just invented. Okay? That's why in his equation, he has to use all the quantum states. If you do all the pure quantum states, you got this equation. But now it's not useful because you cannot calculate all the states, as Sergey just mentioned. Okay? Now, so it's right at that time, in the 50s, 60s, when density function theory becomes available, we can take this, we cannot calculate individually, put in density function theory. That's just, I think it's really because we have these tools available. So this is one basically derived by Gibbs.
Yeah.
And this is from DFT. So basically, to come together is what statistical mechanics have. But now, because in the event we separated them, okay. So we separated the quantum mechanics in this side and the statistical mechanics by Gibbs on the other side. Put them together. That's what we do the measurement. That's what we measure.
Okay.
And also, let's really put all this entropy kind of together as I mentioned here. You see, that's just we didn't realize that's why when we finished that work for silver and iron 3 platinum. We didn't have such deep understanding until because many people ask us questions, and so it took us quite well. Our first paper was 2008, but we only got fully understood it, I think, in my opinion, the last year. So more than 10 years later.
Okay.
I think this goes back to my question of the sampling problem. How well can you describe partition function?
Okay,
it's really DFT makes it work. That's the key. But it's important. It's a very important message I want to mention is that many works, probably literally trying to use DFT to solve this problem. No, DFT alone cannot get heat capacity correct. It only gonna correct is only if only one state or one microstate. That means this equals 0. But that's never happened at finite temperature. Only happens 0 Kelvin.
Yeah. Very interesting. Any other questions, last minute questions for Professor Leo? So if not, then let's thank our speaker again. Professor Leo, it was very educational. Thank you for sharing these interesting results. And it was a pleasure to have you with us today.
Thank you
We'll
very
keep
much.
in touch.
Thank you for the opportunity.
Thank you so much. Bye-bye. So we can end here and enjoy the rest of your day. Bye-bye.
Bye.